next speaker. The Taieb, he will speak on multi-output conformal regression.
Right. Hello everyone. So my name is Souhaib and I'm from Mohamed bin Zayed University of Artificial Intelligence in Abu Dhabi. And I'm going to talk about conformal prediction for multidimensional output regression. And this is a joint work with my PhD student, Victor Deur, and Naomi Desaubry, in collaborations with Matteo Fontana from Royal Holloway London and Yorick Estina also from the University of Mons in Belgium. So we have a paper, so this presentation will be visual, but we have a paper with more technical details and analysis if I choose. All right, so in our setting, both the input and the output are multidimensional. Input has dimension P, the output has dimension D. We have a data set, endpoints, sampled IIJ from D. And our goal is to predict or to generate a joint prediction region for that output Y with the classical conformal prediction properties, distribution free, model agnostics, and also the finite sample coverage. Of course, we also want our prediction region to be sharp, to have informative predictions. Now, because of that, our output is multidimensional, we need to capture the dependencies between the outputs. In the multi-output settings, we have more complex prediction regions, which leads to higher computational complexity. All right, so let me go quickly to the split conformal prediction algorithm that Emric presented beautifully this morning. So we have a data set D, we split it into training, calibration. We build a predictive model using the training set. It doesn't have to be, so the model doesn't produce a point prediction necessarily. You could also produce a distribution prediction. We'll see that some the scores use require predictive PDF or CDF, for example. We define our conformity score. We compute the scores on the calibration set. And then we compute the 1 minus alpha empirical quantile, Q hat. And finally, for a new test point, we construct the prediction region by keeping the points for which the scores are less than Q hat. So that's the split conformal prediction algorithm. And everything is about, in this presentation, everything is about the score. So what type of score can you use in the multi-output case? Quickly, so I think it has already been introduced this morning. So if the calibration set and the test set are exchangeable, then we have the classical marginal coverage guarantee, finite sample coverage guarantee. Ideally, we're interested in the conditional coverage guarantee, but we know that it's impossible in the distribution-free setting. But there are other weaker notion of conditional coverage, including approximate and asymptotic conditional coverage. So that's a quick recap of conformal prediction. Now, before talking about multi-output predictions, let's talk about some conformity scores in the univariate case, right? So I chose these four because you can see that they are based on different predictive models, right? So here we have a point prediction, the mean. Here we have a quantile. Here we have a CDF, and here we have a PDF. Okay. So let's have a look at the visualization and then go back to this course. So this is a one-dimensional case. The input is also one-dimensional. This is my oracle regions. So the absolute residuals, the one we use the means, we can see here cannot capture the heteroscedasticity. It doesn't vary with X. The one with the CDF and the quantiles can capture heteroscedasticity. However, they generate prediction intervals, so we don't capture the bimodality. The one using the PDF, we can see here, can capture the bimodality. However, it's more noisy, and the reason is we need to estimate the CDF of the density values. So you need to do this by sampling. So the message here is you can use different scores and these scores will lead to different geometry essentially for the prediction regions. Okay, so that's the univariate case. I forgot to say that the black, so coverage levels for 20% in black, 50% in green, and 80% in yellow. Now, this is univariate. Let's move to the multivariate case. Actually, I will just have a toy example with a univariate input and a bivariate output. So these are my oracle contours. The goal is to estimate these contours. Okay, let's start with simple methods. So what you can do if you have multiple dimension is just consider D. So if your dimension is D different scores, you compute the regions, let's say intervals. It could be union of intervals. And then you can adjust, you can apply a Bonfollin correction to get the joint coverage. So it's just the Cartesian product of this region, and you get a joint region. Here is an example. So you can clearly see here we have these hyperrectangular regions, which are a bit far from the oracle regions. Right, so here we have a different threshold, conformal threshold, for each dimension. So that's the Bonfollin method. For the MCP methods, we do the same. However, we use another score that will essentially take the maximum of these scores, and we have an additional conformal threshold to recalibrate, let's say, the joint coverage of these regions. And again, it is a Cartesian product of these regions. Right, so I have two simple methods. Actually, if you have, in practice, if you have weak dependencies between your dimensions, then it works actually quite well. All right, so if you want to capture, so if you predict the mean and the covariance matrix, then if you use the score, if you use the Manhawel distance as score, then you can get ellipsoid regions. With the density, so if you have a predictive density, then you can compute highest density regions, and we can show that this has the smallest expected volume. All right, now, what if you have a generative model? So you can only sample from your distribution. So there is a score which essentially samples first from the conditional distribution and then compute the minimum distance between these points and the observed y. And the region are essentially balls that are centered at these samples. And the conformal prediction algorithm will essentially calibrate the radius of these balls in order to get the coverage, right? We can see here that it's not very nice compared to others. We have additional sampling variability. However, if you only keep the points with highest density, then you have a better, you have more stable, let's say, regions. But however, here it requires a predictive PDF. So you need this PDF to rank the points by highest density. All right, so I'll skip this one. So this one is a latent-based approach, and the score is a bit more complicated, but it's related to another one that I will present later. This one is interesting because this is the one that computes the CDF, the CDF of the PDF. And this has an advantage. Your threshold Q hat is not fixed. So it varies with X. Okay, and we can show that this will allow you to have asymptotic conditional coverage. Actually, the previous methods, all of them, I think, had a fixed threshold over X. So it doesn't change with X, right? That's the first one who allows this. However, there is a problem is that it's difficult to estimate the CDF of the density values. All right, so I will talk about two scores that we proposed. Well, essentially, you can generalize this, the CDF of the density to the CDF of any score, right? So we have many scores for multivariate outputs. By applying the CDF to that score, you can essentially improve and obtain asymptotic conditional coverage to any score. So essentially, we have a score here, SW, and we compute the CDF, the conditional CDF of that score has score. There is a star here just to make sure that we understand that this is an oracle quantity, right? In practice, you need to compute this, right? You need to approximate this. So I'm not saying that you will get conditional coverage. Yeah, you got it if you have FW. But in practice, you have to estimate it. And here what we do is we sample from conditional distribution, and then we use the empirical CDF. So that's a new score. So CHDR, so it's a particular case of that score, but you can also build new scores. For example, this one, if you use this, if you have a generative model that didn't have the asymptotic conditional coverage, what you can do is by using this new score, you will obtain it thanks to this CDF of the score. However, here we have additional sampling variability with this PCP score. All right, so previously I talked about the CDF-based score in the univariate case. And here we proposed an extension of that score to the multivariate case. And essentially here you are dealing with an invertible generative model. You estimate Q. So Q is, let's say, a generalized multivariate quantile, right? So you have Z, which is has a Gaussian distribution, and Q essentially will map it to the initial space. And what you do is you compute, it is invertible, so you can compute Q minus 1. So this is the CDF, let's say, and you compute the norm of this CDF. So what you are doing with this score is essentially measuring how, for a given X, how Y conform to X. I know it's a lot to digest, but just the general idea is we work in the latent space. And actually, this is so the DCP, this one, is a particular case of this score, well, in the univariate case. So, and you can show here, so if you take if Q minus 1 is the CDF, and you use D being the absolute value of Z minus 1/2, then you get this score. So essentially, you can actually, if you look at many scores, if you think about how to extend them to the multivariate case, you find interesting new scores with interesting geometry. Okay, if we put everything together, so we have these rectangular regions, we have the ellipsoid. These are density-based. This one has a fixed threshold, conformal threshold. This one has a threshold which varies with X. These four are sampling-based. We can clearly see that. And LCP, this is a latent-based approach. Now, what about bimodality? So here is an example where you have bimodality. This one, well, you cannot capture bimodality here. Actually, if you have union of intervals for each dimension, then you have actually more complex region in that case. So if, for example, if you use HDR for the 2 dimensions, then actually it's more complex than that. Yeah. For the others, we capture bimodality. Of course, this one we can't. And this one, LCP, well, you are applying a smooth transformation to this unimodal, let's say, region, so you cannot get bimodality, obviously, there. All right, in the paper, we analyze the computational complexity, the type of regions, and asymptotic coverage, so I won't go into the details here. Let's have a look at the, well, before that, I just wanted to mention that this is a very active area of research, many scores, many results. Actually, we are extending our paper to a journal paper soon with more results. So if you are interested, drop me a line. All right, so quickly some experiment. So we have 13 data sets, thousands of observations. The input is between 1 and 279, and our output is between 2 and 16. The base predictor is normalizing flow, which can be applied with density-based, sampling-based, and latent-based methods. So this is important because we want to use the same model for all methods. We also considered other base models. The conformity scores were the one I presented. Some methods have some hyperparameters you need to sample. So here we sampled L values, and the ECDF we also used 100. We split training, calibration, testing. So what we do is we compute some kind of conditional coverage error, and what we can see is that, as expected, so the method that achieve asymptotic conditional coverage actually have a better coverage here. MCP, so these methods that essentially has rectangular regions, has a higher error, but actually PC, so the other methods that don't achieve asymptotic conditional coverage have a higher conditional coverage. In terms of computing time, clearly the one that samples requires sampling significantly increase the computational time as expected. Now, in terms of volume, we often in conformal compute the average volume, but you have to be careful because the method that adapts with X, they will increase the size of the region when you have high uncertainty. So they are more adaptive, and they will be penalized by the average, right? Because if you have a very high region for some X, then the average essentially will inflate you will inflate the average. So as expected here, if you look at the mean, then DRCP we know theoretically that it has the smallest mean, but actually the one that achieve asymptotic conditional coverage have a better median volume. So we have to be careful here how to compute sharpness essentially. So let me conclude the talk. So essentially, with the multivariate outputs, we need to capture the dependencies between dimensions. We are dealing with more complex prediction regions, which leads to higher computational complexity. The conformity scores is very interesting when you move to the univariate. From univariate to multivariate, the geometry becomes more interesting. And you can use diverse predictive models, let's say, point prediction, mean, quantile, but also distributional and generative models. Clearly, we have seen the conformity score has a direct impact on the geometry of the region and also on the conditional coverage. Future work. So here is a question. If I give you a distributional prediction, you apply conformal prediction, it will return a region or an interval, right? What I want is I give you a predictive distribution, give me a conformal predictive distribution for which the regions are conformal, right? So that would be great. And actually, we have a paper that tried to do that under revision. But I think this is an interesting direction. Also, what about scoring rules has conformity scores, right? So what about using energy score, variogram score, right? So it feels natural to use conformity scores in the multivariate setting, has conformity scores, and then you will have interesting geometries. Foundation models, so the story about recalibration and calibration is, okay, you fit a model and then it's not calibrated, let's recalibrate it. But think about foundation models and that we are using now with AI. They are built on so many data sets, and then you have to calibrate it on your own data set. So I think recalibration becomes more important. And finally, improving conditional coverage, it's important. And my colleague, Maxime Panov, will talk about it. Maxime Panov will talk about it in the talk. Thank you very much.
Thank you very much. Maybe in the interest of time, Maxime can start setting up, and we can take 1 or 2 questions. Yes, please.
So, thank you. It's really interesting and a very naive question, possibly. But isn't what you're ending up doing very similar to attempting to find a kind of meta model? So, you know, the entire idea is that it's model-free, but now you're kind of, when you show me these pictures, I think of like, oh, how do I actually model those tubes you're showing me? So at the end of the day, how different is it from having to posit a model once you're in multiple dimensions?
Yeah, well, I mean, okay, when you do conformal, right, you have this structure, which is conformity scores, and then you get region, and then whatever, right? But actually, there are some papers, I think not many, who made a link between conformal prediction and recalibration. So essentially, what you're actually doing is essentially you have a model, and you are essentially recalibrating that model. That's essentially what you are doing, right? Even in the univariate or the multivariate is the same, right? You are just improving some properties of your model, not just calibration, but possibly sharpness through that recalibration.
Yeah, so I guess my point is that the sharpness you could think of as a model selection criterion. And so
Oh,
you
yeah.
actually want to select the
Okay.
score that gives you...
Yeah, there are some papers, I didn't cite them, very recent papers, that try to minimize, maximize sharpness. So really they look at the volume as they solve an optimization problem with the volume in it. Yeah, so there are so many directions about the calibration and sharpness. How do you handle it when building these conformal methods?
I can probably go on for
Yeah, we can
but
talk
maybe
later.
we'll
Yeah,
Excellent. Thank you again.
yeah.